There is a piece of advice that has circulated through garages for probably 60 years, and it sounds logical until you understand what it actually does to a modern engine. A ticking engine needs thicker oil. Hot weather means going up a grade. An engine with 200,000 miles should run something heavier to fill the gaps. The reasoning feels right enough. Thicker fluid, more cushion, less wear. Except that chain of logic was built around how engines worked in 1975, not how they work now, and forcing a honey-thick oil into a modern engine does not protect it. It starves specific systems inside it, and the damage does not announce itself until it has already happened. The first place thick oil does damage is inside the variable valve timing system. Every modern engine relies on oil as a hydraulic fluid to advance and retard camshaft timing. Cam phasers receive pressurized oil to rotate the camshaft a few degrees in either direction, optimizing when valves open and close based on load, speed, and temperature. The passages that carry that oil are not large. Some of them route through screens measured in microns, filtering debris before the fluid reaches the phaser actuator. Put a honey-like viscosity booster into that system, and the fluid cannot move fast enough through those passages to build pressure at the right moment. The phaser hesitates. Cam timing lags. The engine management computer detects the timing error, sets a diagnostic trouble code, and the check engine light comes on. Codes P0011 and P0012 are among the most common on modern dual overhead cam engines, and thick oil is one of the causes that shops frequently miss. What happens in the background while the light is on is that the timing chain is rattling against its guide every time the phaser fails to respond quickly enough, and that rattle is wearing metal that no machinist can put back. Here's the part that confuses most people at the shop level. Oil pressure is not the same thing as oil flow. A thick, honey-like oil creates high resistance inside the oil galleries. That resistance registers on the dash gauge as elevated oil pressure, and the needle climbs. Looking at the gauge, the engine appears protected. What the gauge does not show is that the oil pump is moving a fraction of the volume per minute compared to what it would push with a lighter oil because it is fighting that resistance on every stroke. Fewer quarts per minute reaching bearing surfaces means less lubrication, and more critically, less heat removal. Thinner oil carries heat away from internal components far faster than a heavy fluid can, which means thick oil trapped in high-stress zones causes heat to accumulate locally, and the oil begins to break down faster in that exact location. The bearing that looked protected, with high pressure on the gauge and cushioned against wear, is actually running hotter and receiving less fluid than the engineers designed it to receive. That damage mechanism is thermal, not mechanical, and it does not appear in a visual inspection. Cold starts expose the problem most clearly. 2 industry tests address this directly, and most customers at the parts counter have never heard either name. One is the cold cranking simulator, which measures the resistance a given oil offers during a cold start, expressed in centipoise. The other is the mini rotary viscometer, which measures whether the oil can actually pump and flow up through the galleries to reach the top of the valve train in the first seconds of operation. A 0W20 oil, the kind that pours like water at room temperature, is engineered to clear both those tests at temperatures well below 0 degrees Fahrenheit. Thick viscosity boosters fail the mini rotary viscometer at relatively mild temperatures. That failure drops the engine into a dangerous regime in tribology, boundary lubrication. Because the oil cannot pump fast enough, the protective hydrodynamic wedge disappears, leaving the metal surfaces in direct contact. Metal on metal, cam lobe to follower, with no film between them. The wear during those first 15 to 30 seconds of a cold start is disproportionate to anything else that happens during normal operation, and an engine that endures 200 cold start year with oil too thick to pump is accumulating wear far faster than the odometer will ever reflect. The actual fix is not finding the right thickness. Understanding viscosity index is the answer. The viscosity index of an oil is a number that describes how much the oil's thickness changes as temperature rises and falls. Low viscosity index oils are thick when cold and dangerously thin when hot. A high viscosity index oil holds its film across a wide temperature range without becoming so resistant at cold temperatures that it cannot pump. Polyalpha olefin base stocks and gas-to-liquid base oils carry viscosity index ratings well above what conventional mineral oils achieve. Conventional Group 1 mineral base stock sits at the bottom of that range. Polyalpha olefin synthetics routinely climb far higher. That gap determines whether the oil moving through a variable valve timing screen on a cold morning behaves like syrup or like a fluid that can actually reach the phaser before the cam lobe wears. Product data sheets list the viscosity index number. Most buyers never look at it. That number is exactly why the thick oil advice keeps circulating at the parts counter, because the thing that actually matters is the one nobody is checking. What the 60-year-old advice got right was this. Older engines with wider bearing clearances, some running between 1.5 thousandths and 2.5 thousandths of an inch, did benefit from a heavier film weight under high load. The hydrodynamic wedge of oil separating a bearing from its journal needs to fill that clearance to prevent metal contact. That logic held for a flat tappet block in 1972. The advice that kept a 400 cubic inch block running in summer heat is the same advice that starves a cam phaser, overloads an oil pump, and scores a cam lobe before the engine reaches operating temperature. Same words, same logic, completely different machine, completely different result.